Good afternoon, everyone. Okay, I've come to Taiwan. I'm Daniel Liu. Before this session, I have to say apologize to everyone because my native language is Chinese. So my English is pretty basic. Please don't mind about it. Okay, this is my first time to be DerbyCon, and I'm happy so many people interested in my topic. I'm happy to hear and to share our research result to you. Okay, let me introduce me my first. Okay, I come from Taiwan, okay, and working at network security, and my Chinese name is Liu Tso Jen. Okay, I know it is very hard to pronounce, so you can just call me Daniel, okay? I know, the Japanese, Chinese, the different languages are really hard to pronounce. Okay, I have 10 years experience on security testing, about the web application penetration testing, the IoT, and the SCADA. Okay, on security, we have the ISO 17025 security test laboratory. So our laboratory will do the testing for our customer, like the IoT, the SCADA device, and the automotive. Okay, so now I'm in charge of the this security testing laboratory. Okay, our team since 2012, we start to the IoT in embedded system testing, and we found our security at 2014. Okay, since 2012, our team already tests more than 200 devices. Okay, I think it should be 300 by end of this year. Okay, the device include the access point, wireless router, IoT gateway, everything about the IoT and the automotive and the embedded device. So in the beginning, we provide a testing service to help our customer to find the vulnerability. So we use the scanning tool to tell them you have some known vulnerability. But sometimes they will not satisfy with this kind of service. They say, hey, I want you find some unknown vulnerability not discovered by another one. So we try to find a way to do this kind of service. So we choose the fast testing technique. So now the fast testing is one of common and effective testing technique to find the unknown vulnerability. Okay, so simply speaking, the fuzzing test, we just send something wrong or something bad to the target, maybe the application or some network service. Okay, so we send the mail phone data or some very big value, very long string, and monitor the target, monitor the response from the target. Okay, so if there is no response from the target, okay, configuration, maybe we find some unknown vulnerability because the target cannot handle our mail phone pack, and we can crash. The application may crash by some reason. So far, you may know the synopsis, the defenses, and the Bridgestone. They are the famous commercial fuzzing testing software. Okay, both of them support most common protocol like the HTTP, SSL, SSH, and DNS. Of course, our company have our own further to do this kind of protocol fuzzing test. Okay, if you want to build your protocol fuzzing test tool, it's not pretty hard. It's a simple, easy thing. For some protocol like HTTP, FTP, RTSP, okay, this kind of protocol are present in text. So you can just use the sniffer to dump the packet, and you can use the text edit to edit the content to do the fuzzing test. Okay, for some protocol like the SSL, TLS, and SSH, so this is a little bit harder to do the further because these protocols are not non-text protocol. Okay, so you have to do some work to read the RFC and spec to know how the protocol work and its protocol structure. Okay, but for this text or non-text protocol, they are running on the TCP/IP. So you don't need to handle how they translate. How they transfer to the target. You just call the socket and send the data to the target. Okay, this is the easy way to do the fuzzing. But for some protocol like the radio frequency, the Bluetooth, ZB, Z-Wave, or the cellular network, it is very hard to do the fuzzing testing because you have to do a lot of work on how they work, how they transfer the data to the target. Sometimes you may need a spatial and customized software and hardware to do the fuzz testing for this kind of radio frequency or cellular network. Okay, for ZigBee, Wi-Fi, Z-Wave, and Bluetooth, they are already some researchers already released their fuzzing tool on the internet. Just Google the keyword, you can find many GitHub projects, and you can download and compile and use their hardware dongle to do the testing. But for the cellular network, it is the most hardest to build a testing environment because the ZigBee, the Bluetooth, and Wi-Fi, it is very cheap to build a testing environment. But if you like to build a testing cellular environment like 2G, 3G, or 4G, you have to spend a lot of money to buy some equipment to simulate the LTE signal. Okay, so and one day our customers told us, okay, they made a new cell phone in Taiwan. They say they want to do the fuzzing test from the LTE side. Does our security could help them to do this? Okay, we say it's pretty hard, but we think we can do that. So we create this project, and today we're sharing our research result to everyone. Okay, so for fuzzing testing, the most important is to build a testing environment. Without the environment, you can do nothing. You cannot analyze the protocol you want to do the fuzz. So in the beginning, we will try to tell us how we build a testing environment and how we analyze the protocol, and we do the fuzzing on some cell phone. Okay, this is the LTE network architecture. There are three major parts in the LTE network. The first one is the user equipment, we call the UE. So such as your cell phone, your pad, or something can insert the SIM card belong to the UE. Okay, another two is the eNote B and EPC. They are the critical important component in the LTE network. Okay, the eNote B, just like the base station in LTE network. So your cell phone will connect to eNote B, and eNote B will communicate with the EPC. Okay, EPC is the core network in the LTE. It responds for manage mobile activity and route the data to the network. Okay, so if you want to build the LTE network, you have to build the eNote B and EPC in your testing environment. Okay, maybe someone know we can buy like the CNW 500 to build a testing environment, but you can find it's a very, very expensive device. You have to spend 150 grand to buy this device. Our security, we are a startup company. We don't have so much money to buy this kind of device. And the most important, this kind of device are designed for the compatibility testing purpose. They used to check your device can connect to LTE or not. So we cannot send some mail phone or do the fuzzing on this machine. We cannot modify the content. So it's time to do the simulator ourselves. So you can find some results and tutorial on internet. It is not it's not difficult to find. So for eNote B, you just to buy the hardware. We call it SDR, USRP B10. Okay, this is a SDR software-defined radio tool. Okay, and with the open air interface software, the open air interface can control the USRP B210 this SDR to control, to transmit and receive the LTE signal. Okay, to build an EPC server, it is the most simple in this part. You just download and deploy the virtual machine image and make a little configuration. The EPC server will be okay. Okay, once your eNote B and EPC ready, so you can take your LTE phone. Before that, you have to prepare the blank SIM card because each InnoB has a different set with your current telecom carrier. So you have to write the information into the blank SIM card and use the SIM card into your cell phone. Your cell phone will connect to E2B. Okay, so you can check to the environment is working or not. Okay, besides for the research purpose, so we still need to some software to monitor your device, what kind of data it receives. So we use the QXDM, the Qualcomm diagnostic tool. So you can connect to your cell phone to check what kind of data received by your cell phone. Okay. So this is a screenshot, so sorry about the Chinese. So the left image is from the cell phone. You just search available network and you find this 20893. This is that the ID name is simulated by our InnoB. So you just choose this one and you can find the LTE status in your InnoB. Okay, once you connect, if your cell phone can access the internet, it means your LTE environment is ready. Okay, so we can move to the next step to analyze the LTE network and find a way to do the fuzzing testing. Okay, so you can find this is the testing environment we build. Okay, we put the InnoB and EPC on the single server. And we use USB SDR device to transmit LTE signal to the device. Okay, and we will also monitor the signal by the QXDM. Okay, this is our fuzzing tester architecture. So you have to take a more look to the open air interface architecture. So in this picture, you can find the EMB application and MME application. These are two applications are most important part in open interface. So you can check how the open air interface to implement a different layer, like the RRC in an InnoB. The RRC will perform the function like the broadcast, the connection management, and the NAS in MME. It will perform non-radio signaling between the device and the EPC. Okay, so you can find all the different layer implemented by our open air interface. But we can do all the fast testing on different layer. But the QXDN only monitors some channels. So we only do a testing in this channel, like the BCCH, CCCH, DCCH in InnoB and ENM, ESN in EPC. Okay, if you do the fuzzing on other channels that QXDN does not support, we may cannot find what kind of method or what kind of data cause the cell phone crash. So in this research, we only do fuzz testing for this channel. But in this channel, there are many different requests. Okay, because the LTE is quite complicated, the protocol, you must follow the LTE workflow to find which request could be fast. Not every request could be used to do the fast testing. If you set a mail phone data in a wrong time or wrong request, the cell phone will discard the packet. So according to our request, only these 10 requests could be tested by fuzz testing, and you can follow the open source to find which file and which function will handle the BCCH, DTCH, or CCH message, and try to do some little change to add some function to read the data from our fuzzer. Our fuzzer will generate the pattern, and we rewrite the function to read a pattern from our file and send the mail phone data to the cell phone. Okay, this is our testing target this time. LG, Google, Next 5. Okay, you can find the process is the Qualcomm Snapdragon 800. Okay, then this is our real environment. So we store in Node B in this laptop as a host OS, and running EPC as a virtual machine. It's a small, simple, but the most important is the least violent is work. Okay, you can find that this is the device, the Google Nexus 5, and this is the USRP SDR radio tool. Okay, once we start testing, it will read the file from our pattern file and try to generate to transmit the data to the mobile phone. And you can check the data by QXTN. So this is the system log from QXTN. You can check the data like the message type, time, packet length, and the payload. What kind of data we receive? Okay, to receive, so we can know which data really cause the device crash. Okay, so let me see our fuzzing result. So we connect our device to our environment. Connect this Google Nest file to our environment. Okay, so we in our testing, we find there is the last message called authentication request. When the start with 0754, it means the authentication reject. Okay, once the device receives this kind of request, the cell phone will not connect to the network anymore. You can only see the emergency call on your cell phone. Even you switch on and switch off to airplane mode, it still not work and reconnect to network. You have to reboot your cell phone and you will reconnect to a network. Okay, because the environment is complicated, so we use the video to show a demonstration. In the beginning, we change the device to airplane mode. Then you can find, okay, we connect, we switch off airplane mode, and you will connect to, you already connect to our Node B, our base station. Then we switch on the airplane mode again to, okay. The next one, we will start to do the fast testing. We will do a little configuration and try to send the mail phone data by our Node B. Okay, you already started Node B. Okay, so now we will switch off the airplane mode again. Okay, you can see we switch off, and you will try to connect to our base station. So you find the LTE status is show emergency call only. So this in Chinese, but actually it's emergency call only. So even you switch on and switch off again, it still show emergency call only. Okay, so we already use the mail phone data, the authentication request start with 0754 to make the device cannot connect to network anymore. If you want to make it no more, the only way is to reboot the device. Let me get it faster. Okay, maybe not fast enough. Okay, so we reboot and then switch to the airplane mode. Okay, then it can connect to the network again. Okay. Okay. So we also expand our testing research on the different cell phones like the Sony Xperia 3, Asus Zenfone 3 Deluxe, and Asus Zenfone 2. Okay, we find another one, Sony Xperia Z3 Plus. They use the Qualcomm Snapdragon 810. We also have the same vulnerability on it. For the Asus Zenfone 2, they have used another process. It has the same situation here. Okay, so this device are used Snapdragon 800, and this device are also may be affected by this vulnerability. They all use Snapdragon 810. But we have to say this device may vulnerable. We cannot 100% guarantee because we just adopt a company. We cannot buy each cell phone to do a testing and verify this vulnerability. So okay, we find this vulnerability at last December, and we report to Qualcomm, and we have some discussion. The response from Qualcomm, let's say, they aware this vulnerability may exist on some older Qualcomm modems, but they believe they already be fixed in a newer version, in a newer product. But they release the update to the OEM, but some OEM will not update the modem, and the problem may still exist in some device today. Okay. Okay, they also gave us a root cause analysis. According to the CGPP technical specification, they say once the secure exchange of NAS message has been established, they have to pass the integration. If the message not failed to integration check, the UE, the device, your cell phone have to discard this message. But in our research, we find Qualcomm did not comply with this specification, and UE still process this kind of message that failed to integration check. Okay. Okay. I hope everybody liked my presentation, and I have to say apologize again because my English is pretty bad. I'm afraid I cannot understand and answer your question immediately. So if you have any question and suggestion, so you can come to me after this session, or you can reach me by email, LinkedIn, and Twitter. Okay, thank you for your attention again. Thank you, everybody.